Good afternoon. So we arrived to the final topic on the chapter of applications of integration before we move on to a completely separate unit on series. And this is another one of those lessons in which I could just give you the formula, tell you what it is, and just go straight to the examples. But in the interest of some of you, or most of you, who may want to actually, understand more about where these formulas come from, because it might be useful when you actually do these types of applications in other courses like physics, for instance. I'm going to spend some time on how we arrive to that formula. Again, show how the formula comes up in calculus. We're going to start with a more idealized example that doesn't require calculus, just to define some of the concepts like moments or center of mass. And then we're going to finish up with an example. So first of all, this idea of a center of mass is something that most people actually intuitively not only know what it means, it's basically a balancing point. Now it depends on the size or shape of the object, but to make it simple, for instance, if you have an object which is in the form of a thin rod, rigid rod, for instance, then the question is, what is that point, right? If you have a rod like this, what is that point that keeps this whole thing in balance? And for example, and also another thing which most people intuitively understand, I would say even by nature, rather than learning the theory, is that this point, the position of the point, depends, of course, on the distribution of mass. Now, if the mass is equally distributed, so if it's evenly distributed from left and right, now it's easy to figure out that the balancing point or the center of mass is in the middle. But for example, if I told you that in fact, let's say if this rigid rod has the mass concentrated at the endpoints. So let's suppose that the attachment between the two endpoints has no weight. So it's negligible. So the whole mass is concentrated at two endpoints. The mass on the left endpoint, let's call it M1, and the mass on the right endpoint, call it M2. If I told you that the balancing point, so let's say this is a stand that keeps this whole thing in balance, ask yourself which of the two masses, M1 or M2, is heavier. So take a moment to think about, but I trust most people will say obviously M1 is going to be greater than M2 because the balancing point is going to be closer to the heavier mass. So the balancing point clearly depends on the distribution of mass, and the contribution to the balance, so to speak, of a point, depends on the how distant that point is from the actual balancing point, from the center of mass. So how do you actually determine this position? Because that's the question. So if I give you 2 points like this, and to make it even more formalized, let's say these are laid down on the x-axis. And let's say the first mass M1 is at coordinate x1 and the other one at coordinate x2. So the question we're going to address here is, what is the x-coordinate of the point that gives me the balancing point? So let's call the x-coordinate of this point x bar. This is essentially the center of mass for this type of object. And we don't need a different number if the object is idealized in this simplified form. Just two weights connected by a rigid bar of negligible weight. So to find the center of mass, one has to basically equalize, or to sum up the moments, the so-called moments of the, we'll get to that actually later. So to figure out this coordinate of the x bar, one must basically equalize the product between the mass and the distance from the center of mass. So for this system to be in balance, the mass M1 times the distance from the point where mass M1 is located and the coordinate of the center of mass, and this distance, by the way, that's going to be x bar minus x1, Typically, the center of mass is denoted by x bar. So the product between the mass and that distance must be equal to the product between the other mass and the distance to the center of mass. And in that case, that's going to be x2 minus x bar. Because remember, we used to subtract the smaller coordinate from the larger coordinate, right? So x2 is further to the right in this case of x bar. So that distance will be x bar minus x2. So that has to be equal to m2 times x2 minus x bar. So that center of mass, that x bar, must satisfy this property for the system to be in balance. And this gives you essentially the formula or the equation for the center of mass in this case. We can solve for x bar, so we can distribute m1 move this to the left, this to the right. And if we pull out x bar, now we arrive to the formula for x bar, m1 x1 plus m2 x2 divided by m1 plus m2. And you can write this down as a formula for the center of mass in this particular case. And this can be extended to any number of objects if the masses are basically distributed at points of certain coordinates like that. The denominator, basically, this is the total mass of the system, obviously, because it's the sum up. And this, the numerator, is called the moment with respect to the origin. Or you will see later when we move on to points in the plane, because that's going to be the goal, that's going to be the moment with respect to the y-axis. So basically it gives you the balancing point with respect to the origin. In this case, there is no other coordinate because I have only two objects that lie down on the x-axis. But you know, this concept can be easily extended to a system of multiple points in the plane. So basically, let's say we have essentially masses m1, m2, mn at coordinates x1, y1, x2, y2, xn, yn. So each a system of points connected rigidly in which the masses are distributed at each of these points. So for example, if I were to sketch just three of them, you could have a system connected like this with a point of, I'm going to write the mass m1 first, and then at coordinate x1, y1. Then let's say another mass here at coordinates x2, y2, and then maybe some mass here, m3 at coordinates x3, y3. And imagine that this system is connected by rigid bars, but all those connections are of negligible weight. So all the mass is essentially tied up at these points. Then you can use the same concept to figure out the center of mass, which is probably somewhere here, depending on how heavy these masses are, right? So the idea is to find the coordinates of x bar, y bar, so that the system is in balance. Basically, the formula that you see above is going to be just the balancing with respect to the y-axis. So if I involve this formula involving the x coordinates of the points, this will tell me basically how far left or right I should place my center of mass. So x bar will be m1 x1 plus m2 x2 dot 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 mn xn divided by the total mass, which is m1 plus m2 all the way up to mn. And like I said, the numerator now is called the moment with respect to the y-axis. Because it tells you how far you are left or right. So that's why it's called my. And m is going to be the total mass of the system. By the same token or the same method, you're going to find, you can find the formula for the y-coordinate of the center of mass. Same idea. but now involving the y coordinates of these points. And this because this gives you the balancing with respect to the x-axis, how far you are up or down. This is called the moment with respect to the x-axis. And the denominator is the same, the total mass. So just to fix this notion here, let's do a quick example before we move on to the situation when we use calculus. So suppose we have 4 points, let's say, m1 of mass 5 at coordinates -4 and 2. We don't even need to picture these points, by the way. We can just use the formula. The second mass, let's say, is 4 at coordinates 0, 5, followed by m3 equals 3 at the coordinates 3, 2. And then at the other point of where the mass equal to 6 is located, coordinates 1, -2. Is -4 here. So what is the center of mass? Well, for x bar, on the top we're going to have the moment with respect to y, so the summation involving the product of the masses and the x coordinates. So look carefully, follow the mass times the x coordinate where that mass is located. 5 times -4 plus 4 times 0 plus 3 times 3, and then plus 6 times 1 over the total mass, which is 5 plus 4 plus 3 plus 6. So the numerator is -20 plus 0 plus 9 plus 6 over 9 plus 9, which is 18. That gives me -5 over 18. So that's the x-coordinate of the center of mass. And for the y-coordinate of the center of mass, now we follow the products between the mass and the y-coordinate at the point itself. So 5 times 2, 4 times 5, 3 times 2, and then 6 times -2. And the denominator is the same like before. It's the total mass. We did it already. 18. Numerator is 10, 20, plus 6 minus 12. 24 over 18. So altogether, this is the center of mass. All right, so before we move on to the actual, because at this point you may wonder, where's the calculus that I need to? Well, everybody realizes that the mass is not distributed at points. This is a very, very discrete, idealized situation, right? In which there is no mass in between the objects, right? It's just at each point. In reality, the mass is distributed continuously through the object. So what we're going to do, we're going to use essentially calculus to compute the center of mass for objects in the form of a rigid, thin plate, that means a plate of negligible thickness, with a constant density of the material. For known constant density, you're going to have to move on to calculus 3. I'll see you there basically. So stay tuned for the next page. All right, so let's suppose the object that you see here is a thin plate with constant density. And remember the density, and let's denote it by rho, a typical notation for the density, typically is the mass over the volume. But because the thickness is negligible, often the density in cases like this, when the thickness is negligible for the object, density can be given in terms of mass over the area. So keep this in mind, that the density, which is a constant, is given by the mass over the area. And with that in mind, of course, the question is to find the centroid, or the center of mass. top function is y equals f of x. As you can see here, the bottom function is g of x, and the domain is a and b. This is the type of plate or the object we're gonna deal with for the purpose of this section. So you guessed it. How do you do this with calculus? Well, we know how to do this stuff if the mass is distributed at various points. Now let's actually do this by essentially splitting this plate into thin, small strips to which I can compute the center of mass, and then essentially I can consider that those points for these little strips all together will basically have the mass concentrated all together at these points. What you saw before when we computed those moments, m1x1 plus m2x2 plus ... mnxn, so these type of quantities, these will be replaced in this case by Riemann sums. So just like before with other applications, let's imagine we do this partition. We're going to do it with respect to x, obviously. And then for a small dx, we have basically a small piece of the material like this. I mean, dx is the length here, and then this is just a point x on the domain between a and b. And what I'm looking for is essentially to compute the center of mass at this little strip. So we're going to compute the center of mass of that strip and then integrate over it. Or to be more precise, we're going to compute the moments of that, the center of mass of the strip, and then the moments with respect to x and the y-axis. All right, so this strip is nearly a rectangle, because dx is small. This can be approximated by a rectangle. Remember, the density is actually constant. So that means just for that strip, the weight, I mean the mass, is concentrated in the middle of that rectangle. What would be the moment of that rectangle, let's say, with respect to x? That means the balancing point essentially with respect to the x-axis. How far this point should be up or down so that it's balanced with respect to the x-axis. Well, that is going to be the product between the mass of that object, of that strip, and the distance between that point and the x-axis. Now this distance is going to be this, the middle of that segment. And by the way, there's a formula that the middle of a segment is the semi-sum of the coordinates of that segment, if it's horizontal or vertical, right? So for example, the y-coordinate of that point will be the semi-sum of f of x plus gx over 2, the semi-sum of f of x plus g of x. That's the formula for the middle point of a segment. F of x is, of course, the distance between that point and the, this point here and the x-axis. And then the bottom here is from, g of x to the x-axis. So that's the midpoint coordinate, if you want, or the distance between the midpoint and the x-axis. This needs to be multiplied by the mass of the strip. Now, the mass is given in terms of the area times the density, which is given by rho. So that means the area of the strip is going to be dx, the side of the rectangle, and the length of the strip. Now the length of the strip is going to be the difference between f of x and g of x, and dx is the width of the strip, if you want, and then times the density, which is a constant. That's going to be out of the integral. So once again, this will be the area of the strip. That's going to be the density. All together, this gives me the mass, and this gives me the distance to x-axis. So this is the moment. Integrating basically over this term gives me the moment of the plate with respect to the x-axis. Imagine you basically add up, which is to say you integrate from A to B, all of these products. This is the equivalent of summations of these mass times the distance plus mass times the distance and so on and so forth. So the moment with respect to the x-axis is going to be then the integral from A to B over this. And we can move the rho on the outside of the integral because it's a constant. And this product, f of x plus g of x times f of x minus g of x, can be simplified into f squared of x minus g squared of x. And of course the 1/2 in front of it. So that is the moment with respect to the x-axis, which is again the equivalent of m1y1 plus m2y2 plus mnyn in the discrete case that you saw in the previous page. All right, same idea for the moment with respect to the y-axis. Now I'm looking at the product between the mass and this distance to the y-axis. Well, the distance to the y-axis in terms of x is just going to be the x-coordinate of that point. So in this case, it's going to be a faster discussion, so to speak. So the moment with respect to the y is going to be the distance x times the mass of that strip dx, and then integrate over that, and you can write the density on the outside. So x times f of x minus g of x dx. So this is if you want to compute the moment separately. If we want to, oh, and I forgot to mention the total mass that we need later, right? So the total mass, well, in that case, is going to be the area of the strip times the density. So the total mass is just going to be the density times the integral from A to B of f of x minus g of x dx. The integral itself gives you the area, multiplied by the density that gives you the mass. When you actually find the coordinates of the center of mass, which remember for x bar is moment with respect to y over m, for y bar is moment with respect to x over m, rho cancels because it appears on the top and on the bottom. So you don't need to know actually the density if you just need to find the coordinates of the center of mass. So we can write it as a formula here. Center of mass x bar is going to be my, which is the integral from A to B x f of x minus g of x dx over the integral of f of x minus g of x, and then y equals the integral from A to B 1/2 f squared x minus g squared x dx divided by the integral from A to B f of x minus g of x dx. Make sure you write this down because I don't want to write it on the next page when I go over the an actual example. So stay tuned for the example involving these formulas. All right, so let's take a look at this example. So suppose you have a plate defined by these curves, y equals 2 minus x squared and y equals x. So let's see, let's sketch them over here. 2 minus x squared, that's a vertical parabola. I'm sorry, yeah, I mean a parabola, vertical open downward. And this should intersect with the line y equals x. So obviously in this case we have to find the intersection points, right? So that's going to be the plate. So we need to find the intersection points because we need the integration bounds eventually. Beyond that, you don't have to do much sketching. The formulas are can apply them directly. You just need to basically make sure you plug in the appropriate bounds. So to find the intersection points, we set them equal to each other. Let's move x on the left. This happens to factor nicely into x minus 2, x plus 1. So x equals 2, x equals minus 1 are the x coordinate of these intersection points. And we don't need the y-intercepts. I mean, we can, it's not a big deal. The y is going to be minus 1. The y, sorry, x equals x 2 minus x squared. Oh, I'm sorry, I made a mistake here. So x squared plus x minus 2, which splits into x plus 2, which factors into x plus 2 and x minus 1. Sorry about that. X plus 2, x minus 1, x is minus 2, x is plus 1. And if x is minus 2, y is going to be minus 2. And if x is 1, y obviously is equal to 1. So the intersection points are minus 2, and 1, and 1. But the integral will be from minus 2 to 1. Okay. So we're going to have basically 3 integrals to compute if you look at the previous formula, because there is the mass which appears in both integrals, the total mass. So let's start with that, which is the integral from, well, it's going to be the density, which we don't know, the integral from minus 2 to 1 of the top function, which is 2 minus x squared, minus the bottom function, dx. And rho will cancel, obviously, so it's not, I mean, the integral itself is not the total mass, it's times rho, but basically that's the integral you need to find, because rho cancels when you find the center of mass. Let's keep rho on the outside, and then I'm gonna show you how it cancels after that. And then, so we're gonna need this integral, so let's actually take it separately. So minus 2, 1, 2 minus x squared minus x dx. That's the power rule, so that's 2x minus x third over 3 minus x squared over 2. We're going to have a bunch of power rules essentially for the whole problem. 2 times 1 minus 1 over 3 minus 1 over 2. And then minus 4, plug in minus 2, that's 8 over 3. And then 4 over 2, which is minus 2. All right, so let's see, that's going to be 12 minus 2 minus 3 over 6. And that's going to be 8 minus 6. I'm going to do it faster on the next one. So 8 over 3 minus 6, that's 7 over 6. And then 8 minus 18, that's minus 10. And this boils to 27 over 6, which simplifies to 9 over 2. So that's the area, which again times the density gives you the actual mass. Another integral that we need is going to be the one related to the moment with respect to the y-axis. So the moment with respect to the y-axis is going to be the density times the integral from minus 2 to 1 of x times f of x minus g of x. 2 minus x squared minus x dx. So again, if we take this integral separately, distribute x, so that's going to be 2x minus x third minus x squared. And now we integrate, that's going to be x squared minus x fourth over 4 minus x3 over 3. So take a moment to do this on your own, because I don't want to waste too much time on this right now, but plug in carefully. Minus 2 and 1. And this should be 2x minus x squared minus, this should be equal to minus 1 over 2. No. Let's see. 1 second. So I just did it separately because I didn't want to waste too much time with this computation. So this should be minus 27 over 12. And let's just set up the moment with respect to x. So again, that's going to be the density times the integral from minus 2 to 1. 1 over 2, the top function to the power 2. It's still using unexpected. So to the power 2 minus the other function to the power 2, which is dx. So let's see, this integral, we're going to take it separately immediately. So that's going to be 1 over 2. Let's expand it. That's going to be 4 minus 4x squared plus x fourth minus x squared dx. 4 minus 4x squared, I mean minus 5x squared if you combine them, plus x fourth dx. So anyway, if we take this integral separately, let's do it like that. We move the 1/2 out, and then the antiderivative is 4x minus 5 over 3 x third, and then plus 1 over 5 x to the fifth between minus 2 and 1. So plug in 1 and minus 2 and take the difference, and then this integral should be 9 over 5. All right, so we have the moments and the mass. Again, that density cancels out. So when you set up for the formula for the center of mass, so that's going to be my on the top divided by the total mass. So my will be that integral minus 27 over 12 times the density over the mass, which is 9 over 12 times the density. You don't have to carry this density over, but I just want to point out why. It's part of the formula, but it doesn't matter when you actually need to compute not the moments or the mass, but the actual center of mass. So let's see, this simplifies to minus 27 over 12 times 2 over 9, which is 3 over 6. That's minus 1 over 2. So that's the x bar. And then y bar, the y coordinate of the center of mass, will be the moment with respect to x over m. That's going to be 9 over 5 times the density over again 9 over 2 times the density. So that cancels. And you arrive to 2 over 5. All right, so that's it for today. This concludes the chapter on applications of integration, and I'll see you next time when we begin the study of infinite series.